this kitchen extends, there's a shared dishwashing area in the center, but it's mirrored on the other side. What's really interesting about what we can produce an individualized service. We have about 15,000 food and beverage employees. We are the largest food and beverage as an overall part of the Royal Company. We have the most employees in the company. So what amazed me when I first joined the company was the cleanliness of the galleys. So we consolidate preparation into one deck above. So above us right now, there is a few hundred chefs right now chopping away. So we can come down here and kind of see without that bothering us. Any questions about the kitchens at all? No? Okay, so let's do a huge straight back out. We're going to walk up and we're going to finish up in bionic walk.
Has a program that's called 100% repurposing of all waste, which means that all waste that comes down here is either bagged as for direct recycling, so it goes to a direct recycler, whether it's glass, plastics, metal, any of that. It is either donated, landed to shore for reuse, that is something that doesn't have to be processed, just goes direct to reuse, or it can be sent to a waste to energy facility. If it doesn't go through direct recycling, doesn't go through repurposing, doesn't go through donation, we send it to a waste to energy facility. Those of you who are from Southampton, where we boarded, directly across the actual harbor we were at, you saw that dome structure. That is the waste energy facility for the Port of Southampton. All of our waste is actually taken there that wasn't direct recycling. So that's a program that Royal Caribbean has. This ship, when it gets to Bay Ellen, as well as Southampton, will operate under the same premise. So Royal Caribbean as a whole operates under the same premise right now, where the port allows us to actually do it. We are broadening that. Currently, right now, it's in Southampton, it's in Stockholm, and it's up and down the east coast of the United States. We are taking the same program and trying to deliver it and actually work with local authorities, because everything we do when we land, we have to work with the local authority. We're trying to broaden it and take it worldwide. We believe it is the right concept to do. So that is Royal Caribbean stands on the waste facility. If you will see two kind of black poles that have, those are the tops of the two incinerators on board. On board the ship has two incinerators where all burnable waste is actually burned. Burnable waste is small bits of plastic, like very small bits of plastic bags, papers, things of that nature. It is incinerated. Again, the reason why it's incinerated purely is a volume issue. So we incinerate to reduce the size. That ash isn't landed, it is recycled or somehow reused. Through this 100% repurposing scenario, ash is reused in concrete making. So if you don't know how actual concrete is made, they use bits of ash and bits of sand and rubble, so ash goes into the concrete process. That's the incinerator. Over there, kind of opposite of this hole in the middle, you'll see a big V shape. That is the actual can crusher. Cans go in and they come out as blocks, solid, either tin or aluminum. On average, that bag full, just so you know, crushed, is about a ton. Weighs 1 ton of glass.
And how many bottles would you get in? How many bottles?
I don't know the number of bottles. That would be a lot. But so just think about a ton of glass crushed. We're going to land probably 8 bags.
So you reckon 8 tons of glass from a 2-night sailing?
No, this has been collected for...
We haven't landed anything yet.
Good.
60 kilometers.
So
it's
on average is about a 7-day sailing.
Yeah.
About a 7-day
So
sailing.
that's a lot of bottles for 2 nights.
Contributing, don't worry.
So you reckon 20,000 bottles a day?
Up to.
Could be more, could be less, depending on how much fun our guests are having, let's say. How much they're enjoying the cruise. Whether it's from the galleys, from the sinks and showers where you stay, hand wash stations, toilets, medical facility, everything gets gets brought down and is collected in its own collecting tanks. From the collecting tanks is then taken to an actual mixing tank. The mixing tank allows us to take percentages of water to make sure that we have the right mix of water. So 20% from galleys, 20% from showers, 20% from sewage. It gets a very nice mix that goes into bioreactors. This ship has 5 82 cubic meter bioreactors. Bioreactors, anyone knows, are live reactors that contain bacteria. Bacteria break down nutrient load. They work similar to your own stomach. Similar. They have different types of bacteria, but similarly they kind of break down nutrient load. From there it goes to DAF units, dissolved air flotation. DAF units allow us to add a kind of a glue or binder, coagulant. Coagulant binds together all of the suspended solids. We then use dissolved air, where DAF comes from. On the bottom is pumped up so air comes in and kind of grabs this coagulant of solids, floats it up to the top. Then there are arms that kind of scrape off the solids. Solids go into a solids tank, which are then incinerated. All of the clean water then goes to a polishing filter. Polishing filter is a very fine mesh, cleans the water even more. Then the water goes through UV treatment. From the UV treatment, it is then discharged at sea when we are outside ports, harbors, and estuaries, greater than 12 nautical miles, moving at greater than 6 minutes. That is a Royal Caribbean policy, even though the water is clean, and we can discharge it in many parts of the world. Royal Caribbean's policy is that we discharge it when we are at sea. Ultra clean water. I can show you some pictures as we go to the engine control room of what the actual equipment looks like. So this is a picture of it, not the scale. This tank is 33 feet tall by 15.5 feet wide. There's 5 of these on board the ship. So this is a bioreactor. This is one of the DAF units. Dissolved air flotation comes up, screws around. These are the UV filters. If you're from the United Kingdom, you probably know UV very well, from Europe period. Because all of your water, whether it's wastewater or potable water, is treated with UV. Unlike if you're in the United States, it's treated with chlorine. But in the United Kingdom or in Europe period, they use a lot of UV. This picture of where you see the hydro, these are the polishing filters. Within these is a very fine mesh. The water comes in from an actual pressure, goes in, and then it's forced out. So water goes through the mesh, all the solids are kept inside, and then sent to an actual solids tank. You saw the very tops of the incinerators, the shredders. I'll let you get closer here, but this is what it looks like when it actually goes down. It's shredded into very, very small pieces, and it's then incinerated. The ash is taken and actually landed. So this is just pictures of some of the bigger equipment pieces that we have that are basically directly below you. There's also two reverse osmosis plants that produce 800 cubic meters per day. Total capacity of water production on board this ship is 2,400 tons of water per day. So we will end up producing the majority of our water. One of the good things about using evaporators or reverse osmosis is we capture a lot of waste heat recovery. So we actually have one of the engines going to produce all this. Well, instead of letting all that nice energy heat just go out the stack, we actually capture it. We use it to boil water. What I always thought was a very cool fact is water normally boils at 100 degrees Celsius or 212 degrees Fahrenheit. Well, on board a ship, when you use an evaporator, if you do it under pressure, you only have to get to about 70 or 80 degrees. So you don't even have to you don't even have to use as much waste heat recovery in order to boil it from an evaporator's standpoint. So again, we produce the majority of all of our water on board. We do have the capability of bunkering it, but since we have all that lovely seawater out there, we like to make it ourselves.
All of the technical aspects of the ship, from the engines, generators, propulsion, making water, treating water, you name it. The incinerators on board, hot water production, everything is controlled and monitored from here. Obviously a tremendous amount of automation on the ship that allows that to happen. So you have a gentleman behind me who's the second engineer, who is basically on watch and keeping the ship running at an optimum condition. Energy efficiency is obviously a huge part of what we're driving with new generations and new hardware. This ship has several energy efficiency features that are built in. One of them is the air lubrication system. We had done a partial ship trial on the reflection. This ship has a full system. Effectively what we're doing is we're injecting bubbles under the hull in the forward part of the ship, so that as the ship goes through the water, the bubbles actually break up the layer between the ship and the water, and it reduces the friction. And so we saw somewhere between 1 and 3%, depending on the speed and the sea conditions on the reflection, but that was a partial ship system. So we would expect to see better with a full ship plant on board there. So we're hopeful that we'll see greater than 3% on that. And again, 3% on propulsion savings is a lot, because 60% of all the power that the ship consumes on average goes to propulsion. Okay? So energy efficiency is important. It's in the lighting. There's no incandescent bulbs on here. They're all LED or they're fluorescent. That's got a double whammy. One, they draw much less power, but two, they don't generate heat. And if you've got literally 1 million incandescent light bulbs that are generating heat, if you have an air conditioning system, guess what? Now you've got to pull the heat out of the ship with an air conditioning system, and that consumes electricity as well. The appliances on board, we look for, well, one is waste heat. So the ship really almost never has to generate its own hot water, because we take waste heat from the engines. Like your car, our big engines have radiators, and so we have heat exchangers, and we can heat water for showers, we can make steam for galleys or laundry, we can make potable water out of it. We can actually boil seawater and make fresh water through desalination. So waste heat recovery is a big way that we increase the amount of efficiency from every drop of fuel that we burn. The hull design and anything below the waterline has been dramatically improved on the ship. We've, of course, redesigned the hull shape to make it more efficient. We've changed the pockets that house the stabilizers. As a comfort measure, the ship has these stabilizers that basically extend out from the side of the ship that keep it from rocking too much. And of course, even when those are housed, those pockets create a drag, because it's an imperfection in the side of the ship. So we've redesigned those pockets so that there's less drag from the pockets. And the same thing goes from the bow thrusters. There's 4 bow thrusters on the ship, and those are essentially propellers, but there's holes going through the bulbous bow that go all the way across the ship. And of course, if those aren't designed properly, they create drag as well. So we've redesigned those and put grates on, and we've reduced the amount of drag that comes from those dramatically as well. The propellers are a new style. They're actually made out of stainless steel rather than bronze, or bronze alloy that used to be common, or is basically the standard in the marine industry. The pods themselves, which are what actually propel the ship through the water. The ship does not have the traditional, big engine driving a propeller shaft going out of the back of the ship with rudders and struts. It has what's called azipods, which look like a hand drill upside down. They rotate 360 degrees, and the propellers face forward, and so they get the cleanest water. So there's no turbulence, there's no cavitation, and it's the most efficient plant we have for propulsion that we know of. Okay, you don't have any drag or resistance from rudders or skegs or even the shaft. Okay, so that's greatly reduced. Somewhere between 8 to 10% more efficient when you go with an azipod rather than having a traditional propeller system. Again, you're not dragging rudders through the water to slow you down either. And even with the pods, over the years, the company who makes those has made improvements in the hydrodynamics of the hull itself, the hull of the azipod. Okay, so we're gaining efficiencies even from an already very efficient propulsion system. Okay, any questions so far? We're going to cover a lot in a very short period of time. I apologize, but we have a lot to cover.
How much of that technology is unique to Royal Caribbean?
I know other people use azipods. We've effectively, for the most part, that's all we use now. We have some applications that still have a traditional motor, but they're few and far in between. Again, it's a company that's a Scandinavian company that makes these. They're used in other industries and with other cruise lines, so I can't say it's unique to Royal. The air lubrication system has a couple of ships that it's been tried on. This is by far the largest ship that's ever had it. And so we're looking forward to it. We're very hopeful that it'll give us a great deal of savings. So that 3 to 5% that we're hoping for is net of the power required to run the compressors. Because obviously, to blow water under the ship when the ship is 29 to 30 feet below the water line is a tremendous amount of energy, right? That's what, 1 atmosphere, so 1 bar of power, or 1 bar of pressure to push the water out. So that's kind of the energy efficiency. This is a diesel electric plant, which means we have 4 big generators, right, that provide power through generators, go to a bus, and all the consumers come off. And that in itself is a very efficient way of regulating how much power you're providing and how much power is being demanded. So everything goes on this bus, and whether it's the propulsion or the lights or the blow dryer in your stateroom, they all come from the same generators, okay? And we try to match the demand as closely as we can to how much power we have available, okay? The ship has 2 different types of engines. There's 12 cylinders and 16 cylinders. Again, so that we can, by operating the right size engines at the right time, we get the maximum efficiency. Because these engines have a sweet spot, so to speak, when it comes to how much power they're putting out. There's a most efficient spot in the power output. Okay. In lieu of burning lower sulfur distillate fuel, which can be scarce in certain parts of the world and often very expensive, we can burn a more affordable, higher sulfur fuel, but have equivalent or even better air emissions quality by scrubbing the sulfur dioxide and the particulates out of the exhaust gas stream. Okay? And effectively, it is a huge tower because 2 engines go into 1 tower. The tower is 16 meters tall, and it's about 4 meters wide. It's huge. We pump between 500 and 1,500 tons of water an hour through each tower. So a lot of water. I mean, we're talking pipes that are like this big around to pump that much water.
Is that similar to like a catalytic converter on a car?
Well, it treats the exhaust. We do have a ship with the TUI cruises that has a catalytic converter that we've spec'd on that ship to treat what's known as oxides of nitrogen. This is more akin to what you would see on a power plant or a factory that's burning fuel oil. You see the white steam plume coming out. That's because you're pumping in water. In our case, it can either be seawater or it can be fresh water that we treat chemically to make sure that the pH doesn't get too low. And whether or not we're using what's called closed loop, which means that we can charge the system with water and just use the same water over and over and over again. And in order to do that, we have to cool it because otherwise the water would become steam. We have to remove the particulate from it, so any of the soot or ash that's in the exhaust gas gets trapped in the water, and we have technology that allows us to remove that. And then we also have to control for pH. So we add caustic soda or sodium hydroxide, whichever way you want to put it, that keeps the pH in an acceptable level. Okay. We can also go open loop, which means we take pure seawater, we spray it into the tower. Before it goes overboard, we send it through a series of hydrocyclones, which effectively creates a cyclonic effect, spins a centrifugal force, so to speak, and it sends the solids out. The water can leave the ship free of the debris, and we capture the particulate, and we land the particulate. Okay. So that's the scrubber. We have advanced wastewater purification system on board. Basically, we take all the water from the ship, the gray water, the black water, and we can treat it to a standard that's, typically better than most municipal land-based plants are. And one of the new things is, so AWPs, as we call it, is not especially new. It's on all the Royal Caribbean ships. Well, the new thing is that, based on some new legislation that's coming out for ships operating in the Baltic in a few years, we decided to go ahead and install the equipment that's needed on this ship that would allow us to meet those standards. That is still very early in the technology, so we will be working on that, trying to commission that. But it is a new technology that's coming up that we'll be working with the manufacturer on in order to see how well that equipment actually works in operation. It's very easy to have something that in a manufacturer's laboratory and make it work. It's another thing to put it on the ship in real operational conditions and see if it continues to work. That's like we like to say, is it fit for purpose? Okay. Let's see. Nick talked to you about all the solids management. I talked about energy efficiency with lighting, appliances, air conditioning systems. We've decentralized many of the air conditioning systems because, frankly, it just takes too much energy to heat or cool a large amount of air and then push it or blow it throughout the entire ship. Ships used to be like homes that had central air conditioning or central heating. Today we're more like the split systems where you have you're creating cool air where you need it and not trying to push it throughout the entire ship. It also gives us some architectural flexibility as well. 3.14 tons per hour. We have very accurate measuring equipment, to tell you that. It's a big part of it. It's a lot of fuel. It's a big ship.
What's the capacity, the storage capacity of the fuel tanks?
I knew you were going to ask me. Total fuel capacity. Gas, oil, and fuel oil. Find that.
How many people are normally in here? Is it just normally one or two?
At night,
a few chairs, but
yeah, no. At night, you're going to have, well, because you have the traditional engineer, the guy with the wrench, right, working on the engine. But we have to have electrical engineers. We have to have heating and air conditioning specialists. We have to have refrigeration specialists. We have to have elevator engineers. So there's a lot of different specialists that we have to have. We have people who specialize in the power plant. We have people who specialize in the pods. We have people who specialize in this and in that. So we really have a lot of specialists. There's 96 people who work in the engineering department alone on the ship. But that's everybody that keeps the water flowing, the toilets flushing, the engines running, the ship moving through the water, everything. So 96 engineers. Many of them are licensed. Some of them are, unlicensed ratings who are, plumbers and fitters and welders and, like tradesmen kind of people. And then you have licensed engineers who went through years of maritime academies or engineering schools. We do have batteries, but it's not for switching from engine to engine. The system is extremely sophisticated in doing load management. So if we switch from one engine to another, basically what happens is one engine is running at 100 and this one's at 0. The system knows it can actually start bringing them up, and then when they parallel, then they start shedding this one and bringing this one up. It happens all the time. Engines are being started and stopped. We're adding an engine and dropping an engine. One thing we want to do is make sure all the engines have approximately the same running hours. So we're constantly shutting them down, bringing them up. Again, as we speed up, we have to bring another engine online. If you're in, let's say you're in the Caribbean and it's it's cool in the morning and then the sun comes out and it gets really hot during the day, we may have to bring another engine on to handle the air conditioning load. But again, by having two different size engines, we hope to avoid that. If we know kind of what the power demand is going to be for every hour of the day. And so if we need to drop a smaller engine to start a larger engine, we're not running two big engines at the same time. So a lot goes into the power management because you want to be an engine. The most efficient these engines can be is about 85% of their maximum load. That's where they're the most efficient. So it kind of goes up at 85. Anything more than 85, the efficiency starts to go down. So your fuel consumption per kilowatt starts to drop off when they start working too hard. But I mean, speed kills fuel. I mean, just like in your car, you're driving your car, you're driving 60 miles an hour, you're getting 25 miles to the gallon, whatever it is. You go to 65, all of a sudden, oh, now I'm getting 20 miles to the gallon. The ship's the same way, but it's worse because we're a displacement hull. It's known as the cubed root rule for fuel consumption. Whereas as the ship speeds up, the fuel consumption goes like this, rather than linear. Unfortunately, it's dramatic. 1 knot of speed can cost you 30 or 40% more fuel. So that's why we plan our itineraries. That's kind of the software side of this. We have lots of hardware for energy efficiency, but voyage planning, route planning, we have a system on board. It's called NRAM. It's called a Dynamic Trim Assist. And it knows, it's monitoring how much power it takes to push the ship through the water at a given speed. And it's monitoring that, and it's suggesting how we should trim the ship, because it knows that if the ship is trimmed down a little bit at the bow, that it's going to be a little bit more efficient. But again, that changes as the ship's speed changes, and also as, if we're burning fuel, we get lighter where those tanks are. If we're making gray water, people are showering and we're washing clothes and washing dishes, that tank starts to fill up. So the system is constantly saying, okay, you're down at the bow too much, or you're up at the bow too much, and it's giving them literally a green, yellow, or red light. And then the guys on the bridge, the guys on the bridge are transferring fuel, they're transferring ballast, they're transferring potable water, they're transferring gray water all the time. And so we pick up a couple of percent efficiency and propulsion there as well, again through operational measures. But a lot of it comes in itinerary planning. Arriving a half an hour later, departing a half an hour early can make a huge difference in the speed that's required between two ports.